Is going to be on geometrical optics, which is all about how mirrors and lenses bend light. And when it bends light, we see images, objects where they really aren't. For instance, when you look in a plane mirror, you see yourself inside the mirror, and obviously you're not there. That's going to be your image. So, the reason we see things is light from the environment strikes them and reflects off of them. Okay, so for instance, light is going to be coming down and hitting this person's foot. It's going to be reflected in all directions, and one ray of it is going to hit the mirror and then bounce into his eye. So we're going to draw that. And we're going to label it the actual path of the light. The light comes from his foot, hits the mirror, bounces into his eye. The angle of incidence is equal to the angle of reflection. Now, what our brains do when light enters our eyes from this direction, our brain knows that light travels in straight lines. So it's going to extrapolate backwards and think that's where the light came from, and you're going to think, or he's going to think, that he sees his foot back here. So this is the apparent path of the light. Okay? So he thinks his foot is back here. Now, if I take every point on his body, if I took this hand, the light would reflect off the mirror and then go back into his eye. And then he would think it came from back here, so we'd think he sees his hand back here. So he's going to think that he sees his entire body back inside the mirror. And we call that an image, because he's not really in the mirror, it's just what he sees. Now, most of this unit is going to be about finding where an image is and then describing that image. So, the image, in this case, is right side up, okay? It is reverse left to right. You know that when you read your shirt in a mirror, it's backwards. It's the same size as the object, okay? He's this tall, the image is that tall. And it's virtual, and we're going to talk about what virtual means in a minute. Whenever we have a plane mirror, these things are true. It's right side up, same size. Now, if you have a curved mirror, that doesn't have to be true, like a funhouse mirror. You can be shrunk in the mirror, you can look really big in the mirror. You can look right side up, you can look upside down. Now we're going to start talking about curved mirrors now. Okay? These are called converging mirrors and lenses. Okay? It's for a concave mirror and a convex lens. Concave means the light comes into it like it's entering a cave, and convex is the opposite. So convex bows out. So this is a convex lens. You need to memorize that concave mirrors act the same as convex lenses. Both of them are converging. Now, to converge means to come together. Okay? And you'll notice the light that comes in parallel converges to a focus. Here, the light that comes in parallel converges to a focus. There's a use for this, or you might have seen this in each case. This would be like a dish antenna. All of the radiation, all of the radio waves that hit that whole surface get focused down to one point, called the focus, and that's where you put the end of the antenna, is right there. And that works to amplify the signal, because all of these waves are going to that one little point. Same thing here. If you take a lens, like a magnifying glass, the parallel light rays from the sun will converge in one spot, and so you can use it to start a little fire or something like that if you have a big enough lens. They have, when we do the math, we're going to get to the math later, they have what's called a positive focal point. So the focal point is the distance from the mirror to the focus. That's the focal length. For this, it's the distance from the center of the lens to the focus. And in our math, we're going to make it positive for converging mirrors and lenses. And they can form images which are, okay, right side up or upside down. Plane mirror, you're always right side up. But in these, you might be right side up or you might be upside down, depending on where we place the object. You're going to be magnified or shrunk. You can be larger or you can be smaller. There can be real or virtual, both types, and again, I'm going to define those in a bit. Now, in order to find the images, we're going to do ray diagrams. That's where you trace the light, kind of like we trace the light for the plane mirror. For this, we're going to draw at least 2 of 3 lines. Light that comes in parallel, we already talked about that, goes through the focus. Light that goes through the center goes straight through the center, and light that goes through the focus comes out parallel. It works in reverse. It's the same as this first rule backward. And then the image is formed where the rays meet. So here's our first example. Okay? One thing I didn't say is that for a mirror, and I'll make a note of it over here, for a mirror, the center is twice the focal length. So if the center of the curved mirror, so here's the mirror, here's the curve, if I extended that to make a circle, this would be the center of that circle, and the focus is halfway there. Here's our object. We always draw it as an arrow pointing up. It could be the person looking into a mirror, or it could be an object like a candle or a tree that you're looking at in the mirror. We're going to draw at least two of these three lines. I usually do the first two. Light coming in parallel goes through the focus. So you're going to need to get a straight edge to do this and draw the same lines that I might have up here. The first one's going to go in parallel and go down through the focus. So it's going to look like that. The second one just goes straight through the center. Okay, so straight like this. Now the last one, I could draw it if I wanted to. It's kind of redundant, but if I went down through the focus, I would come out parallel and would end up in the same spot. So now you draw your image from the center line to where the rays meet. So they're meeting down here below it, so I have to make it point down. Now my image is upside down, it's smaller, and it's real. It's upside down obviously because it's pointing down, smaller because it's smaller than the object, but then real, we have to describe what that means. So real means the light gets to the position where the image is. The light gets to the image. This ray of light will actually reflect off the mirror and end up down here. This ray of light will actually go through the center, so the light is getting there. But when that's true, I could put a screen there and focus it on the screen, or I could put film there and focus it on the film. Now, we're going to find that every time the object is far away, more than twice the focal length, the image is going to have these things be true. It's going to be small and upside down and real every single time. A use for this is like in a reflecting telescope. If I'm looking at a star in a telescope, the star is very far away, and the image that I form of the star it is going to be small and upside down, and I could put film there and take a picture of it. Our next example. Now, our object is between the focus and the center. So before it was out past the center, now it's inside the center, but still outside the focus. We're going to draw the same rays, so you have to memorize. What are they? A ray that goes parallel is going to go down through the focus, like so. A ray that goes through the center is just going to continue straight, like that. Where they meet, we draw in the image from the axis down to where they meet, so our image is going to look like so. We have to describe it. Okay, it's pointing downwards, so we say upside down. It's larger than the image, so we can say it's larger or magnified. And does the light get to this point? Yes, the light would actually physically reflect off of here, go down through here. The light physically would go through here. So it's going to be real because the light gets to that point. So we'll make note of that. It's upside down, it's larger, and it is real. So a use for this would be in, say, a slide projector. Okay? A slide is kind of small, all right? And we put it near the mirror in the slide projector, and it's going to make a bigger upside down image that I can focus on a screen because it's real. Now, it actually turns out that it is upside down. When you put slides into a slide projector, you have to flip them over and put them in the slide projector upside down so that when you see it on the screen, it looks right side up. Our next example, we're going to move it closer yet. So now the object is inside the focus. So here's the focus, here is the center. Okay? Again, draw the same lines. Lines go in parallel, go down through the focus. Lines that go through the center continue on straight. So it would look like this. Now the problem with this one is they're never going to meet over here. But if we could extend the lines back up this way, then they're going to meet back there somewhere. When I extend them back, when I draw this, I don't do solid lines to show that the light can't actually get there. There's a mirror here. The light can't go through the mirror and get on the other side. So when I send them back behind there, I do it with dotted lines. Now they're meeting back here, and there is my image. Now, I have to describe it. In this case, it's going to be big, and it's going to be right side up. But since the light can't get there, I'm going to call it a virtual image. So right side up, larger, and, if I can get there, virtual. Okay, now virtual meaning I couldn't form it on a screen there. So if you're over here looking at it, you'll be able to see it. You'll see this big image, but you couldn't put it on a screen or on film, okay, and see it. Now, a use for this is in, say, a makeup mirror. Okay, with a makeup mirror, you want to see a lot of the detail on your face, so it's going to magnify your face, but it's still going to be right side up. Okay, example 4, we're going to start working with lenses. It's going to be the same rules. The difference is I have a center now. Instead of being out at twice the focus, it's right in the middle. I didn't have it on here, but you can draw in a center line that goes through that. Okay, we have a focus on each side, all right, because the light's going to go through. So I can put my object on this side and have the light go through and go down through this focus. Okay, or I could have the object on this side, and the light that goes parallel like this would go down through this focus. And you have to be able to realize you could draw it either way. Light that goes through the center is going to go straight through the center. Now, there is one thing about this that's true. When the light gets to this front surface, it's going from air to glass, so it's going to refract. That's what makes it bend. Then when it gets this surface, it's going to go from glass to air, it's going to refract again, it's going to bend again. But when you do the ray diagram, you don't have to show those two bends. All you need to do is draw it straight to the center line and then straight down through the focus. It's not physically what's happening, but it does give you the right answer when you're trying to find your image. So our first ray goes parallel till it gets to the center line, and then we're going to bounce it down through the focus. Our second ray, we're going to send straight through the center. Now, we already know where the image is going to form. It's going to form over here, so I don't need this third ray, but I want you to see it. The other option is, remember, it's parallel down through a focus. The opposite works. If I go down through a focus, I'll go to the center line and then come out parallel. I'll end up hitting in the same spot if I did it very accurately. So now I'm going to draw in my image. My image is right there, pointing down to where they meet. And again, we're more than 2F out, so when it was far away, we always get, with the mirrors, we got this too, a smaller inverted image. So we're going to say the image is upside down, smaller, and does the light get to that point? Yes, light actually does go through the lens and get to that point. So we're going to say it's real. Okay, we have one more example. This time we're inside the focus. I'm not doing all three possibilities like I did with the mirror, but light that goes in parallel, we draw it in until we hit the center line of the lens. It's going to go down through the focus. Light through the center is going to go down through the center, and they're not going to meet over here. So what do we do if they're not going to meet? We draw dotted lines backward until they do. So like so. So now our object, or I'm sorry, our image is going to end up back here. So the image is right side up, magnified, okay, because it's bigger, and it's virtual this time because the light doesn't actually get to this spot. So what that means is you could be over here looking at it and you would see a big image, but you couldn't form it on film. An example of this is a magnifying glass. With a magnifying glass, we hold it close to the object, and then it magnifies the image, and it's still right side up. So that's what we needed to learn for our first lesson on lenses and mirrors. You have to remember that converging mirrors and converging lenses do the same thing. And a converging mirror is concave, and a converging lens is convex.